In today's video, we are going to look at simplifying radical expressions. But before we do that, let's make sure that we have our vocabulary set. So in the typical radical expression, we have a few pieces that we need to be able to identify. Main thing is we've got our square root symbol, or we could call this the radical symbol. And the value that we're taking the root of is called the radicand. So for example, if I was going to take the root of like 64. However, the type of root that we're looking at is a number that we'd usually put up in this top left space, and we call this the index. So for example, if I was going to take the third root of 64, that's where I would write what type of root I'm using. And then this whole expression is called our radical expression. Now, usually when you're looking at these problems, you're used to taking the square root of things. And if we don't have an index written in, that's what we should always assume. So if the index is not written, then it's implied to be 2. Otherwise, you'll have something like a 3 or a 4 or whatever we're using written in. So important that once we're done with a problem, the radicand should never have any perfect square or cube factors, depending on what our index is. So if I'm doing a square root and I have something like a factor of 4 still under the radical, then that's not considered simplified. And that's our biggest thing for this unit. We always need to make sure we have a simplified radical expression. And not only can we do this with any factors, any number factors, but we can also do this with variables. So let's do some practice problems. And then we're also going to practice simplifying multiplication problems as well, just to make sure that our final answer is fully simplified and no other perfect squares or cube roots or what have you can be taken out of our expression. So first, let's look at our basic format. So one thing to remember too is, what pieces, how we can kind of undo our radical. And number 1 looks at that. So in our first problem, for first part of number 1, we have the square root of x squared. And again, don't forget, assume that you've got an index of 2 if you don't have anything written in that space with your radical. So what happens when you take the square root of something that's squared? Well, those are actually inverse operations from each other, and they undo each other. So when you want to undo an x squared, in other words, solve for that x, you always take the square root of both sides. So the square root of x squared would just be x. What would the cube root of y cubed be? Well, that's just y. What about the fifth root of z to the 5th? Again, you're doing the opposite or inverse operation on it. And so any type of root whose index matches that of the exponent of the term underneath or of the radicand, then they simplify each other out. They cancel each other out. Let's look at number 2. So now let's look at some values. So let's take the square root of 75. Now there's probably a couple different ways that you may have learned how to do this. One way is you can do a factor tree for these expressions. But I also too, if you can figure out where the perfect square or perfect cube is hiding, then that's actually a quicker way into the problem. And I know 75, well, that's just the same thing as 25 times 3. And so I tend to go after it that way because I know 25 is a perfect square, and that's going to be the easiest to simplify. So just like in example 1, we said the square root of something squared, it simplifies out. Well, square root of 25, that's really 5, because 5 squared equals 25. So I can rewrite this as, well, square root of 25 is 5, so that can be written outside the radical symbol. And then we didn't have any factor to pair up or to help us, simplify out the 3. So the 3 stays under the radical, and that's our final answer. Now, number 3, slightly larger number, and this is one, I'll be honest, I don't know the square roots or the perfect squares that are factors of this on first glance, since it's such a high number. So start trying to divide out values that you do know about. So that ends in a 0, so I know it's probably going to have like 5 as a factor or something like that. And actually, when I broke this down, I was thinking perfect squares. Well, the first perfect square that I know about is a 4. So when I divided out a 4, I actually got 735. And then I see 735. Well, I know that's a multiple of 5. So if I divide out a 5 from that, well, I got 147. And on first glance, I think 147 is a prime number. But as I started testing out my different factors, again, looking for any perfect squares, again, 4 didn't work, 9 didn't work, but 7 squared, aka 49, that one did work. And 49 times 3 is what 147 is. And so one of the tricks that I like to do too, if I'm going to do factor tree method on this, rather than just being able to understand what my factors are, I tend to cross out anything that I factored out further so I don't confuse it with my available factors that I have to work with. And so I know now I've got this 4 that's a perfect square. Well, square root of 4 is 2. And I have this 49 that's a perfect square. Well, square root of 49 is 7. So both of those can go outside the radical symbol. Whereas inside the radical, I didn't have anything to help simplify out the 5 or the 3. And then any leftover factors, I just multiply them together wherever they are. So I have a 2 and a 7 multiplied outside the radical, that's a 14, and then 5 and 3 inside the radical. So my final answer comes out to be 14 root 15. Okay, 4, 5, and 6, now we've got some variables in the mix. Excuse me. And so, the numbers themselves aren't really that bad to look at. 72, well, that's a little familiar, and that's actually 36 times 2. And so he gives me perfect square. And so when I'm thinking of these, this is how I'm thinking again. Everything that I can simplify out with a square root, that means I'm looking for perfect squares. So I know I have 36 times 2 from our number. Let's see, we have x cubed. Well, that's the same thing as x squared times x, and x squared is a perfect square. We have y to the 4, which, do I have a perfect square for that? Well, yeah, I have a y squared and a y squared. And then what about z to the 5th? Well, I could do z squared times z. And this is why I put crosses through my z's, so you can tell the difference between a z and a 2. So each one of these that's a perfect square can simplify out of the radical. Square root of 36 is 6. Square root of x squared is an x. So actually, I'm going to cross these out as I'm going through them. See, our first y squared simplifies out to a y. Second y squared simplifies to a y. Our first z squared, our second z squared, and then under the radical is everything that was left over that didn't get paired up with something. So we had a 2, an x, and a z left over that weren't part of any perfect squares. And then I just multiply the things that are together either outside the radical or inside the radical. So we have a 6x y squared z squared. And in the radical, we have a 2xz. And again, you'll notice I'm writing things down, even though I know these are not difficult numbers, and you've probably even seen these kind of problems before, perhaps in Algebra 1, although it's been a while. But I'm not trying to keep it in my head. I want to do something to help myself organize. Okay, number 5, 48. And again, if you go through and test out your perfect squares, that's actually a 16 times 3. But wait a second, is this a perfect square problem? Not so much. So this is a perfect cubed problem. So instead of looking for squares on this one, now we're looking for groups of 3 things. And so the 48, let's see, I know that's 3 times 16. But taking apart the 16, well, 3 times 2 times 8. Why do you think I have the 8? Perfect cube. It's 2 times 2 times 2. You can do the same thing with your variables. X cubed, well, that's already in the format that we need. We've got 3 x's multiplied. Our y to the 6 is really y cubed times y cubed. And our z squared, well, I can't take a group of 3 things out, so I'm just going to leave that as a z squared. And so now we're ready to simplify things out. The cube root of 8 is 2. Cube root of x cubed is x. Cube root of y cubed, and I have another. And then everything else has to stay inside the radical. So we had a 3 and a 2 and a z squared left over. And then multiply everything together. So 2x y squared cube root of 6z squared. Alrighty, so number 6, 64, but we're looking at the 6th root. So we need groups of 6 items to make this work. So 64, I think I need to do some work off the side. I know that's 8 times 8. Wait a second. 8's a perfect cube, and each one of those breaks down into 3 2's all multiplied. So wait a second, 64 is a perfect 6th root. So I'm actually going to just write that as 2 raised to the 6 instead of taking up all my space. See, we have x to the 6, already a group of 6 things. Y to the 7 means I can take a group of 6 y's plus an extra, or times an extra. And then z to the 13, how many groups of 6 things? Well, we can take out 1z to the 6, another z to the 6, that makes 12, with a leftover z. So then we can start simplifying. Okay, we have 1, 2 that comes out from 2 raised to the 6th. 1x, 1y, 1z, and another z. And then our leftovers still in the radical are a y and a z. So multiply everything outside. 2x, y, z squared, 6th root of yz. And one of the things that I like to do when I'm writing out these, higher end radicals that have that index is I kind of put my number in the check mark with the radical symbol just to help me organize things. Alrighty, so at this point, just to keep this video a little bit shorter, I'm going to suggest that you now go ahead and pause your video and try out problems 7 through 12. And then you can check your answers on the posted key that's right below this video. Now, in the second part of this video, we are going to look at multiplying radicals. Now, the kicker is on this one, for you to be able to multiply 2 or more radical terms, you need to make sure that you have the same index. So they're both square roots or they're both cube roots. If they're not the same index, then we can't combine them. But we can start playing around with the format a little bit. So for example, in the formula I've got up on here, we've got, the dth root. I was trying to use different values or different variables. If we had m times n under the radical, we could actually separate that out into 2 radicals with the same index. And so we can also go the other direction. So if we notice that we have factors in 2 separate radicals, but they're the same index, then we can actually combine those into one term and then have more factors to work with when we're simplifying. So example 13, we're looking at root 5 times root 35. Well, I know that square root of 35 is actually, square root of 5 times 7. So let's write that out. So this is really square root of 5 times the square root of 5 times 7. Now, each radical by itself doesn't have a pair of factors, but if I combine these into one expression, with a 5 times a 5 times a 7, well, there's my pair of factors, my 5 times 5, or 5 squared. That would be simplified by that square root. And so then I can rewrite that as 5 root 7. Okay, number 14. Let's see, under my radicals, I have 7 and 8, and they're both square roots. So I can technically multiply them. However, I'm not going to have any factors that really help me out with anything other than what's under the 8. But I can still combine things all together, all my values multiplied in the front versus all my values multiplied under the radical. So let's rewrite it like that first. So I have a 3 times a 4 outside the radical, and we have a 7 times an 8 inside the radical. And I'm going to go ahead and break down that 8. Are there any factors of that are perfect squares for our index of 2? 8 is the same thing as 4 times 2, and 4 is a perfect square, so I can actually pull a 2 out from the square root of 4, which leaves the 7 and the 2 still underneath the radical, and then multiply everything together just as we were doing in our previous problems. So 3 times 4 is 12, times 2 gives me 24, 7 times 2 is 14. And so same thing if we're dealing with variables, let's put everything together, either everything out front or everything under the radical, and then simplify from there. So right now, all I have out in front is a 3. But under my radical, if I'm thinking about my values, well, 28, could I use the 4 in any way from the second radical? 28 is really 7 times 4. 4x cubed, well, we have the 4, and then our x cubed, but we're doing squares, so I can take an x squared times an x. I can use my two 4s now. 4 times 4, or 4 squared, undoes the square root. Same thing with the x squared times x squared. We undo with that square root. So I can take those outside the radical. So 3 times the 4, which we simplify out, times the x squared, which we simplify out, and we still have a 7 and an x left inside. And so multiply everything outside and everything inside. So we have a 12x squared times a 7x under the radical. Alrighty. So our last couple examples are getting a little bit more involved, but it's the same type of process. So let's look at our values. What factors do we have to work with? Okay, here we go. So number 16, we've got 4 root 2x times 5 root 6xy squared. Again, everything's the same type of radical, index of 2, so we can combine things as needed. So let's do 4 times 5 from the outside. Inside, we have a 2 and an x, and we have a 6, but I can break the 6 down. That's a 3 times 2. We have an x and a y squared. So look for your pairs of factors. I have a pair of 2's now that I can use. I have a pair of x's that I can use. And now we have a y squared that just by itself gets simplified out. So we already had a 4 and a 5 outside. Now we can take out a 2. We can take out an x. And square root of y squared is y. So what's the only thing left under the radical? The only thing that didn't simplify out was that leftover 3. Everything else paired up. So 4 times 5 is 20, times 2 is 40, x, y, root 3. In our last example, now taking a look at the fact that we have a cube root, we need to make sure that we make groups of 3 factors to be able to simplify. Looking at our first radical, unfortunately, we don't have enough information just with that one alone. So we're going to have to combine our factors with what we see in our second radical. Again, has an index of 3, so we can go ahead and combine those factors. And we have to consider all the factors together to be able to simplify this. So let's go ahead and put everything under the same radical, except for this 2 that we have kind of sitting in the middle. So we have a -2, and then we have a cube root of all of our other terms combined. So we have a 2, we have an x squared, we have a y squared, we have a 16, which if I divide that out, thinking about what cube roots I have, that's an 8 times 2, 8 being a perfect cube root. We have an x to the 5th. So that means I could take out an x cubed and an x squared, and we have our y. So let's see what pieces we can combine now to make, simplifiable factors. So we have our 8 that we'll be able to simplify out. We'll have our x cubed that we can simplify out. We have a y squared plus a y, or times a y, which means, again, we've got our group of 3. And we also have an x squared, which we can combine with one of the x's from the second x squared. So when we do that, see, we're taking out a single x. So that takes care of our x squared and one of our x's here. So let's cross out that exponent. We can take care of our y squared and y, which makes our y cubed. Cube root of y cubed is a y. So that takes care of that one. We have our 8. Cube root of 8 is 2. Takes care of our 8. And then we have that single x cubed, which again, cube root of x cubed gives us an x. Everything that's left over inside the cube root, we have a 2, we have another 2, and we had that single x left over that we weren't able to use. So now let's multiply everything that's out in front of the radical and everything that's inside the radical. So we have a -2 with a 2, so -4. We have an x times an x, which is an x to the, x squared. We have a single y, and then the cube root of 4x. Alrighty, so now video is going to end. Go ahead and do the you try problems and then check that against the completed organizer that's posted below this video. Let me know what questions you have, especially before you start your mini quiz. Again, you only have one attempt on the mini quiz for each lesson this unit. So make sure that you've had enough practice and gotten all of your questions answered before you attempt that. Talk to you later.